Welcome to EGME-331. This is Solid Mechanics. In this video, we are going to review the topic of impact testing. So before we talk about impact testing, let's take a look at what's brittle fracture. Now, brittle fracture is a breakage or cracking of the material into parts. And during this process, we don't see any deformation or visible deformation on the body. In other words, brittle fracture is a sudden, very rapid cracking of the material or the body under stress, where the material has not exhibited any signs of ductility or plastic deformation. So why is brittle fracture important? The primary reason being, unlike the traditional tensile failures, where the material plastically strains under overload conditions and then becomes thinner, undergoes necking, and then finally leads to the rupture. In the case of brittle fracture, there is no thinning, no necking. Instead, the damage mechanism is often caused without any warning, and the resultant failure is a catastrophic fracture. As we can see in this figure here, we have shown a ship that has subject to brittle fracture, and for over a century ago, engineers used to wonder why the ship was subject to a brittle fracture where there was no plastic deformation and there were no signs that it was coming. And then they soon came to a conclusion that the sub-zero temperatures or the extremely low temperatures in the deep sea could have facilitated the brittle fracture. So they could find a relationship between the brittle fracture and the temperature of the temperature at which the material was exposed to. Now let's take a look at what's impact testing and what has it got to do with brittle fracture and the operating temperature. Coming to impact testing, impact tests are used in studying the toughness of the material. So a material's toughness is a factor of its ability to absorb energy during plastic deformation. And impact test measures this ability of the metal to absorb the impact. Now the toughness, as we just mentioned, the ability to absorb energy. For brittle materials, the toughness value is relatively lower as compared to ductile materials. The reason being, the brittle materials can only absorb small amount of plastic deformation and they consequently fail faster than a ductile material. Coming to the effect of a temperature. At the beginning of this video, I mentioned that the temperature has something to do with the brittle fracture. And what we have seen here is, if you take a look at this graph over here, you could see three different materials being shown. The bottom material is a high strength alloy, and then we have the low strength alloy. We can take an example of low carbon steel, and then on top we have an FCC metal. FCC stands for face centered cubic metal. An example would be aluminum. The graph shows a relationship between the absorbed energy and the temperature. As we can see here, for the FCC metal, the example being aluminum, you could see that for all the temperatures that the material is subject to, the absorbed energy remains high, which means the material is ductile. Material's behavior is more or less ductile. On the other hand, if you consider the bottom high strength alloy, you could see that irrespective of the temperature, the material is always behaving brittle. That means the material is subject to brittle fracture. What is interesting here is the material in the middle, the low strength BCC metal or the low carbon steel, where the material's behavior fluctuates or changes from one behavior to another. That means it was at low temperature having or showing a brittle mode of failure, whereas when the temperature was increased, it slowly transitioned from brittle mode into a ductile mode of failure. So if you see the black curve on the left hand side of the graph is more brittle, and as we move to higher temperatures, the graph moves into more brittle zone. So what is so interesting about this graph is that depending on the operating temperature, the behavior or the way which the material fails could change. And this is huge because now we need to factor in the operating temperature for such materials. While designing these materials, we saw the example of a ship when it was subject to extremely low temperatures in deep sea, and that's happening because the material's behavior would have changed from, let's say, more ductile at relatively high temperature to a more brittle state at very low temperatures, and the ship was subject to an catastrophic failure through brittle fracture. Now coming to the impact testing methods or methods to evaluate the impact value or the toughness, there are several methods that exist. The most popular ones being the Charpy test and the ISO test. Here we are going to explain about the Charpy test. The Charpy test measures the total energy absorbed during the specimen fracture, so which is an indicator of the toughness of the material. The standard Charpy specimen, as you can see here, is hit by a pendulum at the opposite side of the notch, and the energy required to break open the sample is broken into two pieces, and this energy is measured. As you can see, the sample standard specimen here, the size would be 10 by 10 by 55 millimeter cube, and it would carry a V notch having 2 millimeter depth at a 45-degree angle, and the root radius should be 0.25 millimeters. At the end of the Charpy test, you would be recording the energy that is being absorbed.